Okay, this is Honors Geo, Chapter 2, Section 5, Reason Using Properties from Algebra. So it's essentially this is our jump into proofs. This is using algebraic equations and algebraic laws that we already know. And actually, you guys have done something similar to this before. We're still going to solve for equations, but now instead of just solving for them, we're going to explain why, or give a reason why we're going to do each step. So essentially, we're justifying each step. This is essentially a proof. So with that, there's certain concepts from algebra that you guys already know, but we're going to refresh a little bit. And the first one is the addition property of equality. So I write it like this. So addition property of equality. And the addition property of equality says that if A equals B, then A plus C equals B plus C, which makes sense. If I have two things that are equal to each other, if I add the same thing to both sides, the equality or the equal sign remains true. Then we have the subtraction property of equality, which says if A equals B, then A minus C equals B minus C. We know these, like I said before, but we've never had to sort of justify it. Now we're justifying, and that's actually what we're doing. Multiplication property of equality. Again, if A equals B. Then A times C is equal to B times C. Now division property of equality. If A equals B, then A divided by C is equal to B divided by C. That's just saying if I add same thing to both sides, it's going to stay equal. If I subtract something from both sides, it'll be equal. If I multiply both sides by the same thing, will be equal, and if I divide. And then the substitution property. And you guys, we're going to be using the substitution property a lot. That's right, as sub. If A equals B, then A can be substituted for B in any equation or expression. If A equals B, then A can be subbed for B in any equation expression. So these are things that we kind of already know. We better know. So using proofs algebraically, as an example, they give us this and they want us to justify each step. So we have 2x plus 5 is equal to 20 minus 3x. Alright, that's our original equation. And then actually, try to, the book writes it as equation. When we're doing these proofs, you don't have to write the explanation. It's just equation and, well, not equation, there's going to be something else here, and reason. This is our justification why we do what we do. So our first part is, do it like this. We have 2x plus 5 equal to 20x, 20 minus 3x. Next thing we're going to do, we're going to add 3x to both sides. Actually, yeah. Let's do it in black, actually. Next thing we're going to do is we're going to add 3x to both sides. 2x plus 5 equals 20 minus 3x. We have to add that 3x to both sides. And then next thing we're going to do is we're going to say 5x plus 5 is equal to 20. Then we can say 5x is equal to 15. Then we can say x is equal to 3. Right, stuff we know how to do. Now, in the world of proofs, we just have to justify it. The first line is always given to us. The problem gives us the scenario. That's the easiest thing. We will always have this as our first line. Our second reasoning, we're adding 3x to both sides, so it's the addition property of equality. Addition property of equality. The next thing we're doing is the 3x's over here cancels, the 2x and 3x over here cancels. So that's, we're just simplifying. And simplify is definitely a justification or a reasoning, even though we haven't wrote it down as one of the things. We can simplify. Next thing we do is we subtracted 5 from both sides, so that's the subtraction property of equality. And the last thing we do is divide by 5 on both sides, so then we have the division property of equality. This is a proof. This is an algebraic proof, but it's still a proof. We proved that x equals 3, and we justify each step. That is a proof. Welcome to the world of proofs. Then we have the distributive property of equality, and we know what that is. That says that if we have addition, multiplication across addition, then we can multiply each term within the addition statement or subtraction statement by the outside term. So distributive property, if A times B plus C, A times the sum of B and C, then I can have multiplication across addition. Whoops. Same thing with subtraction. times v. And again, we already know this. All right, distributive property. Okay. Again, they give us a scenario. Let's see. This is distributive property. We have a negative 4 times 11x plus 2 equals 80. Then we have negative 44 x minus 8 equals 80. Then we have negative 44 x equals 88. And then we have x equals negative 2. Again, solving like we normally do, but now we have to justify. And our justification, first one is always given to us. Then the second reason is distributive property. You can write distributive property like this prop, or you can just write this. We add 8 to both sides, so that's addition property of equality. And then we divide it by negative 44, so that's division property of equality. Again, each step is being justified. This is essentially a proof. This problem is basically the same problem. Alright, so for this they tell us to solve the equation and to justify each step. So let's do that. We have 4x plus 9 is equal to negative 3x plus 2. The next step would be to, I would add 3x to both sides, so I have 7x plus 9 is equal to 2. Subtract 9 from both sides. 7x equals negative 7, and then x equals negative 1. Alright, so justification. First side is always given to us. Here we added 3x to both sides, so that's addition property of equality. We could write the addition property and then simplify and all this other stuff. If we want to be consistent, I guess, with the book, to be step by step, I guess I should write that. So this would be 4x plus 9 plus 2x equal to negative 3x plus 2 plus 3x. So that's addition property of equality. Then we have 7x plus 9 equals 2. That's because of simplifying. And then we have 7x equals negative 7. And that's because we subtracted 9 from both sides, subtract the property of equality, and then we have x equals negative 1. And that's the division property of equality. Yay. So that's that one. Again, it's pretty straightforward. You guys should know how to do this. I'm not too terribly concerned that you don't. Alright, so we have 14x plus 3 times 7 minus x. And that equals negative 1. Again, that's given to us from the problem. Second step would be to say 14x plus 21 minus 3x equals negative 1, and that's because we used the distributive property. Next step is to say 11x plus 21 equals negative 1. That is simplifying or combining like terms. Then we can subtract 21 from both sides. Subtraction property of equality. And then lastly, x equals negative 2. Division property of equality. Alright. Simple enough. Next one. They want me to solve for b. So a equals 1/2 b times h. Multiply both sides by 2. 2a equals b times h. Divide both sides to get to b. So 2a divided by h equals b. Okay, again, given. We did multiplication property of equality, and then we divided. Okay. So yeah, we know how to do that. All right, some more concepts. And this is properties and how they sort of relate to geometry. So reflexive property. And all reflexive property says is that anything is equal to itself. Or, no. Yeah. Duh. Again, I was confusing it with symmetric. Anything is equal to itself. So some number a is equal to itself. That's with numbers. In geometry, we have segments and angles. So we could say that angle AB is equal to itself. And we actually use reflexive property a lot in proofs. Super duper a lot. And then we also do it with angles. Angle of measure A is equal to itself. So reflexive property of equality. These are all equality. And we'll also, when we start doing proofs, have congruency as well. So reflexive property, number is equal to itself, a line segment is equal to itself, and angle is equal to itself. Reflexive. symmetric property of equality. Again, we're going to use these a lot. These are all property of equality. If we have two numbers that are equal to each other, then I can reverse the order. I can say if A equals B, then B equals A. If segment AB is equal to segment DC, DC, CD, then segment CD is equal to segment AB. We're just switching the order. And also for angles, if the measure of angle A is equal to the measure of angle B, then the measure of angle B is equal to the measure of angle A. So we could just switch the number or the segment or the angles if they're equal to each other from right to left or left to right across the equal sign, and they will still be equal. Alright, reflexive property, symmetric property of equality. And then we have transitive property of equality. We will use this property a lot. I repeat, we will use this property a lot. So, three numbers. If A equals B and B equals C, then A equals C. Alright, if A equals B and B equals C, then A equals C. The B's cancel out and whatever's left is left over. This is sort of what we did with in the previous section with the law of syllogism. Basically, it's the transitive property. Alright, for line segments, if AB equals CD and CD equals EF, well then we can say that AB equals CF, EF. Makes sense to me. And then for angles, same thing. If the measure of angle A is equal to the measure of angle B, and the measure of angle B is equal to the measure of angle C, then I can conclude that the measure of angle A is also equal to the measure of angle C. Transitive property of equality. Okay? Alright, using those things in proofs. Here, in essence, is sort of like our first proofy proof. We have this picture over here. We have three angles. Actually, 1, 2, 3. We have 4, 5. I see 6 angles. We have an angle 1 and an angle 3. Notice that the angle 1 and 3 have the curved markings, which tells me that angle 1 and 3 are congruent, and are equal. This is based off the drawing. And then we have this angle 2. We also have angles labeled with letters: CBE, CBA, CBED. We have ABD, ABE, ABC. And what do they want us to do? They want us to use the information to say, they want us to find if ABA is equal to DBC. So here is EBA, this guy right here. They want to know if it's equal to DBC. So before we even start thinking about solving this, let's look at this a little further. I'll try and draw this. Actually, I did that wrong. Do it like this. Alright. Let's do that. And let's say these guys are the same. Call you 1, 2, and 3. Then we got our C. We got our B. Got our A. Got our D. And we got our E. What do they want us to say? They want us to say that EBA, so this guy, so angle 2 and angle 3, is equal to DBC, which is angle 1 plus angle 2. So they want to say that the measure of EBA is equal to the measure of DBC. Okay, well, if you think about it, if I was to add 1 and 2, right, to get DBC, and if I was to add 3 and 2 to get DBC, EBA, since 3 and 1 are the same angle, if I was to add the same angle by the same number, that would make sense. So let's say that angle 1, let's use numbers as a reasoning, is equal to angle 3, right? And let's say that angle 3 is equal to 4. Let's further suppose that angle 2 is equal to, I don't know, 5. So if I was to put numbers in its place instead of angles, I can say that 4 is equal to 4, right? Makes sense because angle 1 and 3 are the same. Well, what if I add angle 2 to both sides? 4 plus 5 equals 4 plus 5. They would also be the same, right? Well, what's 4 plus 5? 4 plus 5 is angle 1 plus angle 2, right? And then the other 4 plus 5 is angle 3 plus angle 2. Okay, and we know that angle 1 plus angle 2 is DBC. And we know that angle 3 plus angle 2 is EBA. So then DBC must equal to EBA. So we have to get to that. That's our reasoning. That's our step. That's our process, and that's what we have to use. And that's what they do over here. So let's look at their proof and their reasoning. So we have our given. Angle 1 is equal to angle 3. That's given to us. This is our proof. This is our reasoning. It's given to us. Well, we know, just by looking at the graph, that angle EBA, I'm just going to write EBA, not measure of EBA for the sake of space, is equal to angle 1 plus angle 2. Wait. Angle 3 plus angle 2. And we know that because of the segment addition postulate, and we talked about that in the first chapter. So segment addition postulate. Okay? That's our justification. Oh, I'm sorry, not segment, angle. I meant angle. Hello? I'll write the angle symbol. Angle addition postulate. Okay? We are given that 1 is equal to 3. So if I know that angle 1 is equal to angle 3, I can substitute 1 for angle 3. And I can say that EBA is also equal to angle 1 plus angle 2 using the substitution property of equality. I can also say that angle DBC is equal to angle 1 plus angle 2. Again, and we know that through the angle addition postulate. So look what we have here. We have that angle EBA is equal to 1 plus 2. We also have angle DBC is equal to 1 plus 2. If A equals B and B equals C, then A equals C, right? They're both equal to the same thing. A equals B and B equals C, then I can say that C equals A. So EBA is equal to angle 1 plus angle 2. DBC is also equal to angle 1 plus angle 2. Since they're both equal to the same expression, then I can say that they're equal to each other. And I can say that angle EBA is equal to angle DBC. And they're equal because of the transitive property of equality. Transitive property of equality. So my first step is given to me. My second step is to say that EBA is equal to angle 3 and angle 2. Since I know that those two angles are equal to each other, I can substitute angle 1 for angle 3 and say that EBA is equal to angle 1 plus angle 2. I know from the angle addition postulate also given to me in the picture that DBC is equal to angle 1 plus angle 2. And then I can use the transitive property. Since both those two angles are equal to the same expression, then they must be equal to each other due to the transitive property of equality. Okay. We have this line segment. We have this line segment. A, B, and we have C, D. We have that CD is equal to AB. We also have this AC right here. And we also have BD right here. They want us to prove, what do they want us to prove? Given the fact that AB equals CD, they want to prove that AC is equal to BD. So we want to prove that AC is equal to BD. Alright. Well, we always start our proofs with our given. It is given to us. We know through the segment addition postulate that AC is equal to AB plus BC. Right? That's given. That's the segment addition postulate. Okay. We also know from the segmentation postulate that BD is equal to BC plus CD, or yeah. If we go back to our initial given statement, again, this is the segment addition postulate. If we go back to our initial statement, and we have A, B, and B, C. They're kind of missing a step here, but that's fine. We can say we have our A, B. This is our first given statement. We have CD. If I was to add the same thing on both sides, then I use the addition property of equality, which says that if I have two things that are equal to each other, if I add the same thing to both sides, then the equality sign remains true. So we can say that through the addition property of equality, they are missing a step that I would put in there, but I guess you can skip it. That is true, right? So what do we have? We already established that AB plus BC in step number 2 is equal to AC. We already established that BC plus CD is equal to BD in step number 3. So if those two guys are equal to each other, I can substitute BD for CD plus BC down here. I can substitute AC for AB plus BC, and I can say that AC I can say that AC is equal to BD. And I can say that because of the substitution property of equality. Yeah. Welcome to the world of proofs. Number 4, ask us to name the property of equality. This one says if 6 is equal to 7 and 7 is equal to 6, that's a symmetric property. And number 5 says J equals KL, JK equals KL, and K equals 12, and then JK equals 12. That's substitution. So if A equals B and A equals 12, then B equals 12. Since they're equal to each other, sub number. Sub. 6, something is equal to itself. Oh no, I'm sorry, this is transitive. If A equals B and B equals C, then A equals C. I'm sorry, transitive property. And then for 6, something is equal to itself, that's reflexive. Okay. Okay. That's this section. Hope you have a great rest of your day.